Hi everyone, in the previous video we gave a formal definition for deterministic automata and I have the definition written right here. So I have Q, which is my set of states, I have sigma, which is my alphabet, my set of symbols that I use, I have S, which is my start state or initial state, I have F, which is a set of final states. Remember, there can be multiple final states in automata. And I have delta, which is my transition function. And here's how we define the domain and range of delta. It was from Q cross sigma to Q. So it takes a state and an alphabet and it gives me a state. So that's my deterministic automaton. And in this video, what we are going to try and do is modify this definition for non-deterministic automata. So the first thing we need to account for in non-deterministic automata is epsilon moves. So let's say I have a state Q1 right here. It can go on epsilon to Q2. So I give no input and it makes a transition from Q1 to Q2. And my transition function right here does not account for that because it says that it has to be from Q cross sigma to Q. So I can have something like let's say Q3 comma the alphabet 0 and this going to let's say Q4. This is actually possible according to this definition that I have right here, but something like this, which is Q1 and epsilon going to Q2, this isn't allowed according to this definition because epsilon is not an alphabet. So it's actually very simple to account for epsilon moves. The only thing we have to do is we define delta as being from Q cross sigma union the set containing just epsilon to Q. So when I do this, then this example right here, Q1 comma epsilon going to Q2 actually fits because I added the epsilon right here. So that's all we have to do if we want to account for epsilon moves. The second thing that we want to account for in non-deterministic automata are multiple transitions. So let me first just get rid of this right here. So for our multiple transitions, what do I have? I have some Q3 which can go on a 0 to Q4 and it can go on a 0 itself to Q5 as well. So once again, this can't be accounted for because my transition function needs to give me one state, which isn't the case right here, because if I take Q3 comma 0, then it will give me Q4 as well as Q5 and not just a single state. So to account for multiple transitions, what do? We just say that it goes from Q cross sigma to the power set of Q, because when I say power set, what does it mean? It means that I'm taking all subsets of Q. So if I say that delta goes from Q cross sigma to power set of Q, this power set of Q will definitely contain an element which is Q4 comma Q5. So this actually accounts for my multiple transitions, this one right here. And if I want to give a more complete definition now for my non-deterministic automata, the rest of the things remain the same. My Q is my set of states, sigma is my alphabet, S is my start state, F is my set of final states. The only thing that changes is my delta is now from Q cross sigma union epsilon to power set of Q. So remember that the power set of Q is going to have 2 to the power n elements if n is the number of elements in Q. So that's all we have to do to formally define a non-deterministic automaton. And one thing that I want to talk about at this point is the start state in non-deterministic automata. Sometimes we also say that it can be a set of start states, although we can always have automata with a single start state, and that's what we are usually going to do. But in theory, it is possible to have multiple start states in a non-deterministic automaton. So that's another thing that we do change sometimes. So we represent it with a capital S, and we say that this is my set of start states, and we can always change this to epsilon moves. So let's say this is my start state right here, which is q0, and I have an epsilon move to q1, I have an epsilon move to q2. This, some people might say, is the same as having start state q0, start state q1, and start state q2, and then continuing my automaton right here. So this is also valid. We could say that S can be a set of start states in non-deterministic automata. So this isn't wrong, but we'll just stick to a single start state as much as possible. And that's it about the formal definition of non-deterministic finite automata. In the next video, we'll take a look at some tricks that we can do with automata to convert them from one language to another, how to take union of languages using a simple trick. So we'll see that in the next video. Stay tuned for it.